So your homework was kind of jumping around a little bit. So we're going to do the concept reviews first for that section because I think that'll be a little bit easier. So concept review number 3. So let's do that one first and then we'll kind of shift around from that. Alright, I put my post-it notes so that I moved them. Alright, so concept review number 3. I'm on the wrong page. Why must the pressure of a gaseous collected over water be corrected? Alright, so the answer is that a gas collected over water will be saturated with water vapor, not just the volume of the gas. And so the actual pressure of the gas is the total pressure minus the partial pressure of the water vapor if you want to figure out what's just the pressure of the gas. Alright, that was number 3. So let's go over to application number 1 now, right underneath it. Alright, so application number 1. Consider the three gases. So we have 3 different gases. We have dichlorine, we have carbon tetrachloride, and then we have radon. I don't think it's going to show up, I think that's too small. Let me write this again. We have chlorine, carbon, tetrachloride, and then we have radon. Alright, so it asks you which, according to Graham's law of diffusion, which would you expect to diffuse the fastest, and which one would you expect to diffuse the slowest? So remember, Graham's law says if you have a heavier molecule or a heavier atom, it'll diffuse slower than a lighter atom. Kind of like if you give the same amount of energy to a bowling ball or a ping pong ball. If I were to take a ping pong ball and throw it, and take that same amount of energy and try to throw the bowling ball, the ping pong ball will move farther and it'll move faster because it has more energy compared to its mass. So looking at these, so you'll need to look at the weight. So if you look on your periodic table, I gotta flip over there. So if you look on your periodic table, you will notice that chlorine, let me get over there. This is why I should use post-it notes more. Alright, well, if you look at for chlorine, chlorine's weight is about 35.45 atomic mass units. So for chlorine, it's about 35.45 AMUs. Carbon tetrachloride, so carbon is 12 plus 4 times this, so that's a lot heavier. Then radon, if you look for radon, you can find it in the noble gases. It has a 222 AMU. So this one's the heaviest, this one's the lightest. So that's why this one will diffuse the fastest, this one will diffuse the slowest, is because it's based off that atomic mass units or those weights for it. Alright, now let's get into your math problem. Your math problem was going back to page number 73, I believe. Let me get out my post-it note for that one. So over on page number 71, I was close. Application number 4 for that one was practice with your ideal gas law. Alright, so for number 4, what is the ideal gas law first off? It's an equation that you need to know. What is the ideal gas law? Alright, so for this one, remember it's PV equals nRT. So that's the equation for the noble gas law. So that's the equation. So PV nRT. Now remember, what does P stand for? Pressure. What does volume stand for? Sorry, what does V stand for? Volume. What does N stand for? Number of moles. What does the R stand for? This one you're going to have to memorize. 0.0821 liters per ATM over Kelvin per moles. Alright, so remember, you do need to know that so that way you'll know your units for it. So 0.0821. That's the R. Now what does the T stand for? Temperature. Good job. Alright, so this is the equation that you have to use for it. Alright, so let's calculate the number of moles. So what are we finding? Moles. So we are finding in. I'm making sure you can still see it. I didn't mark where the line was. It's about right here. So I'll write the value for R over here. So 0.0821 liters per ATM over Kelvin per mole. So that's what R is. So you can see it. Alright, so now it's asking for, we're finding this one, number of moles. So assuming of nitrogen, if it behaves in a 2.25 liters. Alright, so let's plug in our values for it. it says 2.25 liters. Can I use liters in this equation? Yes, I can. Since it says liters, I can go ahead and use liters. So I'm just going to write it on here. So 2.25 liters, because that's the correct units. Let's see, at 25 degrees Celsius, can I use Celsius in this equation? No, it has to be Kelvin. So because of that, I have to convert. Alright, so 25 degrees Celsius plus 273.15 becomes 298.15. Gonna move this down so I don't have to worry about writing. I'll realign it in a second. 298.15, so that's the temperature for it. I'll shift it up in a second, I just want to make sure I have room. Alright, and then it says at 780 torr, assuming the gas behaves ideally. Alright, can I use torrs in this equation? Nope, I cannot. I have to use ATM. So how do I go from torrs to ATM? Right, I divide. So if I start off with 780 torr, I divide by 760, that'll tell me how many ATM, or how much an ATM that I will get from it. Alright, so this will give me 1.026 ATM. So putting this down here, so 1.026 ATM, that's the pressure for it. So now I'm going to go ahead and put it all in proper spot. So instead of copying down the units, I'm just going to leave it as a 0.0821. Temperature, 298.15. So those are all of my values. I'm just going to shift it down some more. I'll realign this later. Alright. So that's all of my values, but I have to get in by itself. So how do I get this in by itself? Right, I divide. So I take all of this and I move it over here and divide by it. So 0.0821 and then 298.15. These cancel out. Alright, so to solve this, it's 1.026 ATM times 2.25 liters divided by 0.0821 divided by 298.15. So all of that together, your answer comes out to, yeah, you can still see me, I just want to make sure. So your answer comes out to 0.0943, that's not a 943. So 0.09430, and then it keeps going. So for this one, I want to know, okay, how many sig figs do I put this into? So looking at what I'm starting off with, I'm starting off with 3 sig figs for the volume. I'm starting off with 2 sig figs for torrs and 2 sig figs for the degrees of Celsius. So because of that, my answer has to be in 2 sig figs. Remember, 780, no decimal point, only has 2 sig figs. And since it's multiplying and dividing, I go off the number of sig figs. So my final answer is 0.094. Remember, these two zeros don't count because they are to the left of the first non-zero decimal point. My units for moles are just moles. So 0.094 is the final answer for this problem, moles for it. Alright, I'm going to go ahead and fix that because it's going to bother me now if I can't adjust it. Okay, thank you for your patience. Alright, so that's for your homework. Now, you notice I have classwork written on the board. You might have thought that was for junior high. Nope, that's for you, because I told you you need to be studying. So, for pages 60 through 71, you want to be studying those terms and definitions. So take about 10 to 15 minutes, maybe. There's not that many terms and definitions on pages 60 through 71. So copy down the bold term and the definition 3 times each, as many as you can, as fast as you can. Now hopefully some of them are pretty straightforward, so that way you remember them. This will help you to study as you get ready, because it's Friday and you haven't had a quiz yet this week. So make sure that you're using your time properly. So go ahead and copy down pages 60 through 71, the bold terms and definitions. I'm going to come back and review with you, but make sure you're using your time properly. So study. Go ahead and pause the video so you can study. That'll give me a chance to erase my board. hopefully you pause the video and come back now. Alright, so there are 5 parts to the kinetic theory of matter. What are they? So, molecules of a gas are in constant motion. What's another one? The molecules of a gas undergo elastic collisions. The temperature of the gas is directly related to its kinetic energy. The volume of the gas is negligible compared to the total volume of the gas. Or your book points out how they go there, that the gas molecules are negligible in volume compared to the volume of the gas. Basically, if you're talking about the volume of the gas, I mean the whole volume. And the number 5, or part number 5 to it, the gas molecules have negligible attraction between them. What do you call a gas that obeys every part of the kinetic theory of matter? An ideal gas. So, a gas that exactly obeys the assumptions of the kinetic theory is an ideal gas. Alright, what is the equation for kinetic energy? K E equals 1/2 mv squared. What's the equation for pressure? E equals force over area. So make note, pressure is defined as a force or a push per unit area. Kinetic energy, note the 2 equations for them. Alright, what is the SI unit for pressure? Pascal. Who discovered atmospheric pressure? He also invented the barometer. Evangelista Torricelli, good job. What is the name for the device that's used to measure atmospheric pressure? I said it a minute ago in my question. Barometer. What's the name for the barometers that don't have mercury on the inside? They may have that flexible diaphragm instead. Aneroid barometers. Alright, so there are 3 units you can use with working with atmospheric pressure or with barometers or with manometers, things I'm never using for pressure in that regard. So if I have a millimeter, I'm going to write over here, if I have 26 millimeters of mercury, how many is that in torr? 26, good job. If I have 26 torr, how much is that in ATMs? I did not check this. Alright, that comes out to 0.034, 266. So that would be ATM. Remember, you divide by 760. If I have 1 ATM, how many torr do I have? 760. Or how many millimeters of mercury do I have? 760. Good. What's the device that's used to measure the pressure of a gas as compared to the atmosphere, or just compared to itself? Manometer. Good job. Alright, so if the manometer is open to the atmosphere, and the gas shifts towards the atmospheric side, alright, which one's stronger, gas or the atmosphere? The gas. So do I add how much it's moved by to the atmosphere, or subtract how much it's moved by from the atmosphere? You add it. What if it shifts towards the gas? Which one's stronger? The atmosphere. So do I subtract how much is moved from the atmosphere, or do I add it? You subtract it because it's weaker than the atmosphere. What if it's a closed manometer? Do I care about the atmospheric pressure at all? Nope. So just how much it's moved by, that's just how much, that just tells me what the pressure is. Alright. What does Boyle's law say? Boyle's law says that the pressure and volume are inversely proportional, or they are opposites. If one goes up, the other goes down. What does Charles' law say? Charles' law says that volume and temperature are directly proportional. If one goes up, the other one must also go up as well. What's the equation that combines Charles' law, Boyle's law, and a Montan's law, technically, all into one equation? This is the practical one we use. Combined gas law, what is it? I'm gonna write it over here. P1 times V1 over T1 equals P2 times V2 over T2. Good job. So that's another equation that you need to know. Let's see. What is temperature at STP, or standard temperature and pressure? What is the temperature? 0 degrees Celsius, 273.15 Kelvin. What's the pressure at STP? 1 atm. Good job. Alright, what is the law that says when measured at the same temperature and pressure, the ratios of the volumes of the gases react hydrogen with 1 volume of nitrogen, I'm gonna get 2 volumes of ammonia. Just saying at a constant temperature and pressure, the ratio of the volumes of the gases in that reactor that are formed are products of small whole numbers, just those ratios. What law is that? Alright, Gay-Lussac's law, so make a note for that. Alright, what's the law that says that equal volumes of gases at the same temperature and pressure contain the same number of molecules? You have a number named after this guy. So the volumes, so equal volumes of the gas at the same temperature and pressure contain equal number of molecules. Alright, there's Avogadro's law. Alright, now that we have Avogadro's law, and we'll notice that, okay, for gases that behave very close to ideal, at STP, at a standard temperature and pressure, they have a certain volume per mole. So at STP, you have a certain volume or liters per mole. What is that molar volume? This is another one that you need to know. So 22.4 liters per mole. So just make a note for that. For if you have a gas that's at STP and it has the same number of molecules, that if it has 1 mole, it'll take up 22.4 liters. So for gases that behave very close to the ideal, the molar volume at STP is 22.4 liters per mole. This only applies though to gases at STP. Alright. So the ideal gas law, what's the equation for the ideal gas law? I'm gonna write it down here. Yeah, you can see it. Alright. PV equals nRT. What's P stand for? Pressure. What's V stand for? Volume. What's N stand for? Number of moles. What's T stand for? Temperature. What's R stand for? I'll write it up here. 0.0821 liters per ATM divided by Kelvin times number of moles. So you don't have to know the units like per se, but you do need to know that, okay, these are the units that I need to use for my equation. If you use torrs instead of ATM, it's not going to be right. So definitely note these are the units for it. So 0.0, you can't see my decimal point. 0.0821. Alright. What do you call the process of mixing molecules of one substance to another by random molecular motion? Diffusion. Alright, whose law, or what's the law that says that lighter molecules diffuse more rapidly than a heavier molecule? Graham's law of diffusion. So just saying, hey, if you have a heavier molecule and a lighter molecule and they have equal amount of energy, the lighter molecule will move faster. Alright, so if you realize now that you want to study a little bit more, you can go ahead and pause the video again and study again if you need to. So, but don't leave yourself too long. So if you realize that you want to rewind part of it and hear part of this again, you can, but make sure you come back. Alright, assuming now that you're back from studying, you need to put away everything. So all of your textbooks, everything should be off the table or off the desk or off your bed or wherever it is you're watching these videos. So you only need out a piece of paper and a working pen. You're not going to need a calculator today, so I want to check your math on Monday before we start having quizzes over it, but we're going to go over it on Monday. So you don't need a calculator, you just need a pen and a pencil. So you need a pen and a piece of paper. You don't need a cover sheet for obvious reasons. But make sure everything is cleared off just like you do at school. So don't have your textbook out, don't have your textbook open. Textbook should be put away. You can put everything else away so you have some nice neat space to work with on your desk or on your table or kitchen table, wherever it is you're sitting at, the kitchen counter. So clear everything off besides just that piece of paper to take your quiz on and then a working pen. So everything else should be put away. At the top of the paper, write your name so I know whose is whose whenever I print these off. I can kind of tell whose is whose by handwriting, I just don't want to. So make sure you write your name at the top so I know whose is whose, and write the date for it as well. You can just write chemistry quiz, I'll worry about the correct numbers later on. So just write your name, the date, and chemistry quiz, and then number it 1 through 10 like how you normally do in class. So it's the exact same thing that we do in class, you're just doing it at home. Alright, so if you really need to pause the video to go get a piece of paper or something, go ahead and pause the video and come back, but don't listen until the quiz until you're ready to actually take it. So if you realize you need to go get something and come back, you can. Alright, so let's go ahead and let's go then. So questions number 1 and number 2, write down any of the 5 parts of the kinetic theory of matter. I don't care the order, so write one part in question 1, write another part in question 2. So there are 5 parts to the kinetic theory of matter. Write one part in question 1, another part in question 2. Pick the ones you can spell. Alright, number 3 now. What do you call a gas that exactly obeys the assumptions of the kinetic theory? What do you call a gas that exactly obeys the assumptions of the kinetic theory? What do you call that gas? Alright, number 4. What do you call the device that can measure the atmosphere? What do you call a device that can measure the atmospheric pressure? Remember, those are up there, so you can't have those. What do you call the device that measures atmospheric pressure? Alright, number 5. What is defined as a force or push per unit area? So, F over A equals what? So what is defined as a force or a push per unit area? What is this equation used to find? I'll look it up. You can have that. Alright, number 6. If I have 1 ATM, how many millimeters of mercury do I have? So if I have 1 ATM, that's how many millimeters of mercury. Alright, number 7. What law says that pressure and volume are inversely proportional? What law says that pressure and volume are inversely proportional? Alright, number 9. What is the SI unit for pressure? What is the SI unit for pressure? Oh, I think I'm not on number 8. I'm sorry, that's number 8. What is the SI unit for pressure? Alright, number 9, theoretically at 0 degrees Kelvin, what should the volume also be, or what should the volume be at 0 degrees Kelvin? I held up 2 zeros by accident. So, if you had 0 degrees Kelvin, or absolute 0, what should theoretically the volume also be at absolute 0? Thinking about what law would help out with that. So if you're at absolute 0, what should your volume also be? And then number 10, at STP, what is the temperature? So if you're at STP, that's standard temperature and pressure, what is the temperature? Alright, if you need something to go back and rewind it to hear a question again, you can go do that. But if you're going ahead and done, you can go ahead and put that off to the side so that way you won't forget about it. So just put it off to the side so that way you can give it to mom or dad, whoever it is that is submitting your work. So that way you can send this to me as soon as possible. So don't forget about it, put it off to the side, ask them to send a picture of it later. Alright, so let's go ahead and let's get back into it. Alright, so talking about Dalton's law of partial pressure is kind of where we left off. I want to practice with the ideal gas law first. So, talking about the ideal gas law, hopefully we've got the equation for it, that you want to note, sorry, it's being glitchy. Alright, you want to note the equation for it as well as practicing for it. Now, Ms. Radasky told me that this shows up better in the video, so hopefully it does. So, I believe it is showing up a little bit better for it. So just make sure though, just comment or tell me if it's not showing up, or if you think that this is worse, try to contact me and let me know and I'll swap it back. But this is supposed to show up and pop a little bit better in the videos. Alright, so let's practice solving these with the ideal gas law. So not the combined gas law, the ideal gas law. I want to make sure we have more practice with this because we kind of ran out of time yesterday. So we ran out of this one, we ran out of time for practicing with this. Alright, so looking at it. So a refrigerator has a volume of 1,100 liters. The temperature inside the refrigerator is 3 degrees Celsius and the air pressure is 1 atm. How many moles of air are in my refrigerator? So, practicing with this one. Now remember, what is the equation for the ideal gas law? PV equals nRT. Alright, so plugging this in, you want to plug in your variables, kind of like how you do with the combined gas law. You want to figure out, okay, what do I have so I can figure out where I'm going from it. Alright, So it says I'm starting off with 1 ATM for the pressure, so the pressure is 1 ATM. Can I use ATM in the ideal gas law? Yes, I can. So ATM is the correct unit. Alright, so it says I have a volume of 1,100 liters. So volume 1,100 liters. Can I use that unit? Yes, I can. So that's in the proper units. Alright, that's me. How many moles? So that's what I'm finding. So I don't know how many moles I have yet. R is still 0.0821. I'm going to leave off units just because it's going to get tiring writing that over and over again. But liters per ATM divided by Kelvin per mole. Alright, and then it says the temperature is 3 degrees Celsius. Can I use Celsius? Nope, it's got to be in Kelvin. So 3 added to 273.15 becomes 276.15. So those are all of my units, and now I just have to plug them into my equation. Alright, so it's 1 ATM times 1,100 liters equals N R 0.0821, 276.15. Alright, so how do I get N by itself? Divide, good job. Remember, it's the entire top divided by the entire bottom. So it's 1 times 1,100 divided by 0.0821 divided by 276.15. This becomes out to N equals 48.518 moles. Now, looking at sig figs, since I multiply and divide, I have to go off the number of sig figs. But looking at this, alright, this has 4 sig figs, this has 3 sig figs, this has 3 sig figs. So, what should my answer be? How many sig figs should be in it? We don't worry about the R value because that's the defined value. Alright, so the answer should be in 3 sig figs. So the answer turns into N equals 48.5 mole. So that's the answer for this one. So 48.5. Alright, try to do the next one by yourself. Try to work as fast as you can. So pause the video so that you have time to practice it on your own. Alright, well hopefully if you're back now watching this, you've already tried this. So let's go through it. Alright, an oven has a temperature of 250 degrees Celsius, an air pressure of 1 atm, and 26 moles of air inside of it. What is the volume? Alright, so the temperature 250 degrees Celsius, can I use that? Nope, I gotta convert. So, 250 plus 273.15, the temperature turns out to be 523.15 Kelvin. So 523.15. R is still 0.0821. Alright, so it says the temperature, the air pressure of 1 atm. Can I use ATM? Yes, I can. Alright, and it says and 26 moles of air on the inside. Oh, so I'm finding volumes. I don't know what volume is. So number of moles, it has 26 moles on the inside of it. So I'm finding the volume. Okay, good, you can still see that. Alright, so plugging this into my equation now. So P, 1 ATM, I don't know what B is. Number of moles, 26, 0.0821. Let's see, temperature, 523.15. Alright, how do I get V by itself? Right, I divide again. So divide by 1, or that'll cancel out anyway, but we'll just move it over just so that way I get V by itself. Alright, so 26 times 0.0821 times 523.15 divided by 1, but that won't change the answer. So that becomes what? Alright, V equals 1,116.715, and I don't want to write the rest of it, but it keeps going. So 1,116.715. Alright, now how many sig figs do I have? Looking at this one has 2 sig figs, this one has 3 sig figs, this one has 2 sig figs. Technically this is a counted value, so I don't have to worry about it, but this one has 2 sig figs as well. So let's go ahead and let's change this into 2 sig figs. Well, No, I would still count this one, even though this seems like a counted amount, I would still count that one. So 26 moles. So changing this one into 268, how do I change this into 268? So it's 1,100, no decimal point, and since we're in volume, what should my units be? Remember, according to R, that constant, what does my volume have to be in? Liters. Perfect. So 1,100 liters. Alright, so that's practice with the ideal gas law. So be sure to ask me on Monday if you have questions with it. Alright, flip back in your textbook now, talking about kind of the idea of Dalton's law of partial pressure. I think I talked through this or introduced it maybe yesterday, but it was super quick. So make a note of Graham's law of diffusion. If I have a heavier molecule and a lighter molecule will diffuse faster if they have equal energy. Alright, Dalton's law of partial pressure. What Dalton was saying, okay, if I have a balloon, or if I have an object like the air where it is a volume of the air of gases on the inside. So let's say I pump up a balloon with a bicycle pump and I fill it up with gases from the air. So what gases will it have on the inside of it? It is from the air. Alright, you're going to have some oxygen, you're going to have some nitrogen, and you're going to have some carbon dioxide and some helium and some other gases. So it's not like just one gas on the inside of it. So Dalton's law of partial pressure was saying each of those gases want to spread out from each other as much as possible. And so because of that, all of those pressures together equal up the total pressure of my balloon on the inside. So that's what he's talking about, that each gas behaves as if the others aren't there, because each gas is to separate from itself as much as possible. So each gas occupies partial pressure of the whole. So you don't have, like my balloon, a section of oxygen, a section of helium, and a section of carbon dioxide. They all want to spread out from each other as much as possible. So each gas is exerting its own partial pressure on my whole balloon. And so he said it's each of those partial pressures all together equal the total pressure of my balloon. So that's what he's saying. Each gas in a mixture of gases expands to occupy the entire volume of the container and exerts a pressure, the partial pressure that is independent of all the other gases. And then the actual law for his, the pressure in a container filled with a mixture of gases is the sum of all the partial pressures of all the gases in the container. This principle is known as Dalton's law of partial pressures. Basically, you add up all the partial pressures together to get the total pressure. It's that simple. Next page. So your book shows you the equation for it, and they use some little subscripts to help make it a little bit easier. But they're just saying that the pressure of the total of the gas. Nope, I'm gonna run out of room because the poles are right above my balloon. So the pressure of the total volume of the gas will equal the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, etc. So it's literally an addition problem. You add up all the total pressure, you add up all the pressures together to get your total pressure. It's that simple and it's that convenient for it. All right. So let's practice with this really quick, just because I know this seems, well, that's really basic. Yeah, but let's practice just in case, just to give you a little bit of help with it. All right. All right, the air pressure at the top of Mount Everest is a different mixture of gases and then from sea level because it's too high. The following of different pressures of gases: oxygen is set as 0.076 atm, nitrogen is 0.13 atm, helium is 0.038. What is the total pressure of the gas? You might really see something like this on the exam, so make sure you do try and don't just try to do it too quick. Alright, well, since Dalton's law says that you really just add them all up, looking at the pressures, it's 0.076 atm plus 0.13 atm plus 0.038 atm. You just add them all up together. The total comes out to 0.244 atm. Now remember, for sig figs 4, addition, do I go off the number or do I go off place? Right, I go off place. So for this one, the 13, that's why this one has to be rounded to the hundredths as well. So 0.24 atm. That's the answer for this type of equation with Dalton's law of partial pressure. Alright, let's look at the second type of problem for it. So if you have a pressurized cylinder of nitrogen and oxygen in the basement for some random reason, and the total pressure is 13 atm, and oxygen's partial pressure is 5 atm, what's the pressure of nitrogen? So this was a little bit different, but if the total pressure is 13 atm, and oxygen has a pressure of 5 atm, what's the pressure of nitrogen? It might be that simple, so just make sure that yes, you do try it. Now, this is a simple, I'll just break a problem. But if it's the total pressure is all pressures of the individual gases, if the total pressure is the nitrogen pressure, I'll put in for nitrogen, plus the pressure of oxygen, which oxygen has a pressure of 5 atm, how do I find the pressure of nitrogen? Right, you just subtract. So 13 subtracting 5 turns into 8. Now again, for this one, because this is in the 10 spot, this one would also be in the 10 spot. So 8.0 would be the pressure, or atm. So that's the answer for this problem. So I know this seems really basic, but you want to make sure you know how to do it. Don't go too fast to where you're not getting it. Alright, so that's the idea of water vapor though. So looking on page 72, talking about water vapor and partial pressure, an easy way to get a gas by itself is to bubble the gas into an upside down bottle filled with water. So you fill up a bottle with water, a jar. I can't draw it upside down like they did. So if I fill up my beaker with water, we'll draw a beaker. That's decent. So if I fill up my beaker with water and then I flip it upside down and submerge it and then put a tube underneath it to pump out all the water, I'm just gonna have just my gas on the inside of a beaker. We're gonna watch some labs later where they do that. So because of that though, you have a tendency to get water vapor on the inside of it, and so you have to subtract out the water vapor from the inside. So your book points out the pressure of the gas in the bottle equals the atmospheric pressure, but you have to figure it out based off the how much water vapor is on the inside of it as well. So you take Dalton's law of partial pressure and they condense it a little bit. So it's the pressure, the total pressure equals the pressure of the gas plus water vapor on the inside of it. So whenever they do this, whenever they boil it, because the water has heat in it, it has a tendency to get water vapor or steam on the inside. So that's part of the reason why you have to subtract out that water vapor. Alright, your book points out at different temperatures, water has different amounts of vapor pressure because different temperatures will increase the amount of water that evaporates. So that's part of the reason why, if this is on your exam, I will give you the chart or tell you what this chart says. So you do not have to memorize the chart. Don't try to memorize the chart. You don't have to. But that's what it's talking about for this one, to where you just subtract out what the water vapor is at that given temperature. So, like for example, for my practice problem for this one, here it is. Nitrogen, come back mouse. Not see my mouse at all. Alright, well, nitrogen was collected over water at 16 degrees Celsius. The air pressure is 790 torrs. What's the pressure of nitrogen? So they will boil the boil the water up to the pressure on the inside of the container equals the pressure on the outside. So your book points out they do this whenever sufficient gas has been collected, the pressure inside and outside of the bottle are equalized by raising or lowering the bottle, so the water levels on the inside are the same. So whenever they do this technique, they know that the pressure, whatever is on the outside of the atmosphere, is also the pressure of the inside on the inside of the gas. So if the atmospheric pressure is 790 torr, that means that the pressure of the gas must also be they have to figure out what the pressure of the gas is and must give it away. So if the pressure of the atmosphere is 790 torr, that's the total pressure. That's the total pressure of the gas and the water vapor on the inside. So 790 torr. That's the pressure on the inside because it'll equal the atmospheric pressures. But they don't know there's pressure of the gas and there's the water vapor. So we're not sure what the pressure of the gas is, but we can figure out what the pressure of the water vapor is. So if it's at 60 degrees Celsius, look at your chart to figure out, okay, at 60 degrees Celsius, how much pressure is that? Now if this is in torr, should I use the ATM side of the chart or the torr side of the chart? Right, the torr side of the chart. So at 60 degrees Celsius, water has 13.6 torr of water pressure of water vapor on the inside. Alright, so how do I find the pressure then? Right, I just subtracted it out. So 790 minus 13.6 comes to 776.4. Alright, so for this one, I said 790 with a decimal point. So that's what I need to round to the ones place. So rounding to the ones place for this one, well technically, did I give a decimal point? Oh, I did give a decimal point. I didn't change that in my answer. Alright, so rounding to this one, to the ones point becomes what? 760. Alright, so that's the answer for this problem. Alright, let's practice one more at the top of the page. So it says a sample of oxygen collected over water at 23 degrees Celsius occupies 480 milliliters at an atmospheric pressure of 743 torrs. How many moles of oxygen were collected? So this one's kind of going to combine the two ideas together. Alright, so first off, I have to figure out how to solve this problem, or figure out what is the pressure of my gas on the inside. The sample of oxygen collected over water at 23 degrees Celsius occupies 485 milliliters of atmospheric pressure at 743 torrs. Alright, so the atmospheric pressure is 743 torr. So looking at the chart, I have to figure out, okay, how much pressure will water, or how much water vapor will water have at 23 degrees Celsius? Well, 23 degrees Celsius, now since this one is in torrs, I'm going to do this in torrs as well. So that's 21.1 torr. The pressure of the oxygen plus the water vapor, 21.1 torr. So I subtract 21.1 from 743. That gives me 721.9 torr. But it's not just asking me just to finish there. It's asking me to say, okay, how many moles of oxygen do I have? What's the only equation we have so far in this chapter that has to do with pressure, volume, moles, and temperature? Right, the ideal gas law. So we're going to have to come back to that. So this is in torrs. Now can I use my ideal gas law with torrs? Nope, it's got to be an ATM. So how do I go from torrs to ATM? Right, I divide. So 721.9 divided by 760, that'll give me my ATM. So I'm going to go ahead and erase these so I can write in my answer. Alright, so 721.9 divided by 760 gives me 0.9499. I'll worry about sig figs later, so I'm just going to leave it like this. Alright, so the next thing is asking me, I have to plug it into my ideal law equation. So go and make my problem together to get the rest of my information. So sample of oxygen collected over 23 degrees Celsius. Alright, 23 degrees Celsius, can I use that? Nope, gotta be in Kelvin. So 23 degrees Celsius plus 273.15 turns into 296.15 degrees Kelvin. Occupies 485 milliliters. Can I use milliliters in this equation? Nope, it's gotta be in liters. So converting over 0.485 liters. At an atmospheric pressure, I did this one. Alright, so R is what? 0.0821, don't forget. And it's asking me how many moles, so I'm finding N. So plugging everything into the proper spot, so 0.9499 times the volume, 0.485. Number of moles are 0.0821 times 296.15. Alright, so that's everything in the proper spot. How do I get N by itself? Right, I divide. Alright, so I multiply 0.9499 times 0.485 divided by 0.0821 divided by 296.15. Alright, the answer comes out to 0.0189 mole. So checking for sig figs now. I have 2 sig figs with the degrees Celsius, 3 sig figs with milliliters, and 3 sig figs with torr. Traditionally, most times you ignore what the Celsius is. They don't really count that as number of sig figs. For your exam, I always make sure that if I want a certain number of sig figs, I make sure the Celsius that you won't get tricked or messed up by it. It also comes they put their answer into 3 sig figs, not 2. So putting this into 3 sig figs just comes out to this as their final answer. So for me personally, I would put a 23.0 if I wanted 3 sig figs just to make sure that that's clear. But if you put this in 2 sig figs, it would be 0.019. But this for 3 sig figs is fine since a lot of scientists, they don't count the temperature of Celsius as part for sig figs. Alright, so your book points out, last thing on page 73, whenever the phrase collected over water is used, be sure to correct the pressure, not the volume, for the presence of water vapor. You have to use that chart to figure out how much pressure of water is on the inside of the container if you see the phrase collected over water. So your book's just pointing out the volume of each gas. The volume of each gas is a mixture of the gases is the same of the inside of it. So because of that, you have to subtract out the water vapor. If you see that phrase collected over water, that means you have to subtract it. But I will give you the chart for the exam if you need it. So you don't have to worry about it per se, but I will give you the chart. So if you notice, collected over water, use the chart that I give you to solve it. Alright, so that wraps up everything for your exam. Alright, your homework for tonight is going to be a little bit longer. So this lesson's a little bit shorter, I believe, depending on how long you pause to study and for the quiz. But I'm going to go ahead and give you your homework. Alright, on page 75, you're going to do the application 2 and 3. So application 2 and 3 on page 75. On page 76, you're going to do problems 1, 5, and 6. So on page 76, 1, 5, and 6. On page 59, you're going to do problem 2, D through F. So it'll be practicing with balancing equations again. So all together, page 75, applications 2 through 3. On page 76, problems 1, 5, and 6. Then on page 59, problem 2, but only the section D through F. So D through F. Alright, we're going to have a Zoom class on Monday. So if you need help with this math, be sure to come and ask me. I can't check very well through this if you understand it or not. So make sure that you attempt the homework and that you do your best. Write down all of your math so that way so I ask you, what did you do? You can tell me what you did. Don't just say, oh, I got this answer. Well, how did you get it? What did you do? I don't know. I can't help you. So be sure to write down what you did for each test. So I can tell you what you did wrong. If you just tell me I got this answer and I don't know, well, I don't know what to tell you. I can't help you fix it. I can show you how to do it correctly, but that's it. So make sure that you write down all of your processes over how you did it so I can best help you out so we don't waste a lot of time with the Zoom meeting. Alright, you have a good day and a good weekend. I hope you have a great